So today we were actually going to do a detailed discussion on friction factors. Let me just get the... So we will actually define friction factors properly. So last time I just did sort of an introduction so we get the feeling where we are going for. And essentially we defined that friction factors is going to be something that will help us extend any upscaling concept to possibly turbulent flow as well. So essential application would be, okay, if I know that I have a tube of certain size, that is likely in the turbulent flow regime, okay, can I actually predict a pressure drop in that tube that I might expect given its physical parameters? And that's something that is very easy if you have laminar flow. We have all of the analytical expressions you could possibly imagine, but for non-laminar flow, you might be actually measuring the velocity, but you might not be having a very good gauge on what the pressure drop might be. So you want actually something that you would like a predictive correlation that can actually give you that number. And that's where basically friction factors come in. So but in order to be able to do that, basically the way it was done is correlating a whole lot of experiments and figuring out what that correlation should be that is then predictive for that flow. So our motivation again is to have correlations or predictions in any type of flow regime for some very well-known geometries. All right, so basically I'm going to put a title. So I will repeat the definition that we had. So our motivation, basically finding a proportionality constant that helps predict friction losses in any flow regime. And this is something that knowing that basically the way we classify similar flows, we don't classify them just based on viscosity. We don't say, oh, there's viscosity is small and therefore then any kind of viscosity contribution is negligible. No, we actually have to go and classify flow numbers, not just flows, not just based on viscosity, but a combination of parameters which are all together in Reynolds number as a dimensionless constant. And last time I basically transformed the Navier-Stokes equation into a dimensionless form that basically shows that I can have that I can basically do that, and that Reynolds number is the number that I should be looking for when I'm basically classifying similar flows. So this is something we will need to do. So basically we will need to do this based on geometry and fluid characteristics combined. So not just fluid characteristics and not just geometry characteristics separately. So they have to be actually done together. So just to remind ourselves, so last time I actually threw in a formula that we will use to define it, and it went something like this. So we said Fk is equal to AKF So this is used for the definition of friction factor. So it's not a law. It's not something that we have, Navier-Stokes. It's not like a Navier-Stokes equation or anything like that. I'm simply defining friction factor using this formula. So this is my friction factor. And in Fk, I'm actually saying, okay, Fk is the kinetic or dynamic part of kinetic dynamic part of the force that fluid exerts on my geometry walls, okay? That fluid exerts on my solid walls. So typically what you have is that there is some total force exerted by a fluid. There is a static part to it and kinetic part to it. So this is the fluid force exerted by stationary fluid. And then the rest of it is the kinetic part. So if in our flow around the sphere, we had the buoyant force, which was there regardless. And then we had the drag force, which was all of the basically kinetic parts that are combined together. So that's one example. So for instance, buoyant force. So we're looking at Fk specifically. And then A here is some area characteristic for the flow, for the geometry. And K is kinetic energy density, meaning energy per unit volume. So typically we know that kinetic energy I'm defining for an object as 1/2 mv squared. So kinetic energy density will be 1/2 rho v squared. And question is then, what is v? Okay, so we need some sort of characteristic or average velocity for the flow. Okay, so typically of the form. Oh, I don't mean to scare anybody with this. So it's typically 1/2 rho v squared, where this is some characteristic velocity. Oops. So this is the part where we will actually have to go geometry by geometry, and every geometry has its own customs and definitions. So we will start with tubes. Okay. Tubes. Specifically, we will look at the circular tube. So basically in circular tube, okay, I am wondering what is my F going to be, or what is my friction going to be. So first I have to actually define myself this characteristic surface. So A, so if this is my tube, okay, I typically have some P0 and PL at the end of it. Distance L. So I have some pressure drop, and this is my generalized pressure, so I have any gravity effects included in there. And I have a tube of certain diameter, so diameter is 2 radii. So then the characteristic surface that is taken for tubes is the wetted surface of the cylinder. Okay, so by customary to take wetted surface of the cylinder. Okay, so that is equal to 2RBL. So perimeter times length. And when defining kinetic energy density, we're taking 1/2 rho and average velocity vz squared. So it's important to define these things in terms of something that we can measure. Okay. I can measure the geometry stuff. Also, I cannot necessarily always measure the details of my velocity profile, but I can measure the average velocity, right? By measuring the flux and dividing by the area. Okay. So those are the things that we can measure. So now what is my FK? Okay. There's two ways to look at this problem. I can actually just try to compute. So I basically integrate my tau RZ over the area that is affected, and I will get that. Or macroscopically, okay, any kind of the force that fluid exerts on the walls in a tube is balanced by what? Pressure drop difference times the areas exposed to that pressure, correct? To get the force. So basically I have this P0 minus PL times R squared P. And actually if I go and, so there are two ways to look at it, and one is simply P0 minus PL R squared P, because this pressure difference times area has to balance the force exerted on solid walls or the friction force. And this actually, if I actually went to compute the friction force for the flow that I know, which is the laminar flow, if I throw in this definition of integration of tau RZ, I would get the same. So essentially, I would have to do, to see just a second, I will open a new one. I was trying to squeeze it in there, but no. So if I actually computed Fk is equal to 0 L 0 to 2p, tau Rz at R is equal to R, and then I'm integrating in cylindrical coordinate system, so I gotta do this. This is my area element. Okay. So this is my shear stress integrated over my wetted perimeter. Then this would actually indeed be, so this is P0 minus PL over 2L times radius. If you go quickly remind yourself what is shear stress. So basically once you do this integration, you would get the same number. Okay. So indeed, this type of pressure difference times the area balances the fluid forces, and that part checks out. But the first reasoning is simply the macroscopic force balance reasoning. Okay. Okay, so this basically then gives me a way to define F. So if I know what my Fk is, okay, my F is Fk divided by AK, and I already defined what area and K I'm going to be using. So basically I'm going to do P0 minus PL, R squared P, divided by area, n times 1/2 rho VZ squared. So it's essentially P, so it's R over L. All of these things, for any flow, I can measure. Okay. So this is actually going to serve as a definition. So if I went and did the experiment, all of these things I could measure, and I could compute what F is for any given flow. Okay? So this is then a good definition of something that I can use to correlate experiments. So this is going to be definition, and it's called so-called fanning friction factor. It's also often written in the following form. It's written as 1/4 diameter over L, and then P0 minus PL. And this 1/2 is kept just simply to remind everybody that this is the energy density. So this is definition of a friction factor for cylindrical tubes It's also called fanning friction factor. It consists entirely, so the idea is all required to compute F are parameters I can experimentally measure. That Fk, that kinetic part of the force, the drag force, you can't measure it directly, right? So we went kind of indirectly to find out something that we can measure. So Fk I can compute if I have the formulas, like analytic formulas, or some way to figure out the force balance. But if I don't, this is basically, well, and we threw in that force balance to actually define the force in terms of things that we can actually experimentally measure, because force directly I cannot measure. Okay, so this is something, this is the data that I can collect from experiments. And when I collect, I try to correlate. Okay, so the idea is F is, so F is collected or computed from a wide range of experiment. Okay. And correlated with Reynolds numbers. And once I have these correlations in place, they can be used as predictive correlations for anything new that I'm trying to design. Okay? So if I'm going and designing a system of pipes and I'm wondering what my friction losses are, whatever pipe diameters is that I'm going to use, I'm glad that there was tons of researchers since 1960s that have been basically measuring all of these flows. And those correlations and tables we have, so I can figure out what my friction losses are going to be, so I can figure out, well, how big of a pump I need to get to pump stuff through the system. Okay? So this is essentially the use of the data like this. And then once correlations exist, we can use them to predict friction losses in anything new we come up with. So let me just remind you of how it's done. Is everybody done with the writing? Just to show you the graph. Yeah. Okay. So basically this is the graph that summarizes all of these experiments. So there's a friction factor that is computed for a range of experiments. We don't see the points here. Okay. Now, and we're going to get through this in a second. For laminar flow, I have the formulas. I can compute stuff. I basically know what my average velocity Vz is for laminar flow. Okay. That's, what was it, chapter 2.3 was it, 2.1? Whatever was the flow in a tube chapter. Okay. So I have that formula for average velocity. Okay. If I actually throw that average Vz formula in there, I'm going to get that my friction factor for laminar flow is 16 over Reynolds. So for laminar flow, we have no doubt that friction factor is very nicely correlated with Reynolds number. Okay. Now for any other flow, I might have doubts. There's analysis done for turbulent flows. For turbulent flows, they might change in time, so there has to be a little more careful analysis done. You also have to have a very long tube to figure out any entry and exit effects that you might have. Technically, it's not just that you have dependence on Reynolds number. There is some dependence on the ratio of the diameter to the length. But it's not a terrible assumption that basically you're just correlated with the Reynolds number. Okay? So we are not going to go into details of that analysis. There's some of that, and we're in chapter 6 right now, so there's some of that analysis for turbulent flows done in chapter 6 if you're interested. But essentially, we're still assuming that the assumption for still holds that I have a very good correlation for Reynolds number. And the way it's fitted to experiments is that turbulent flow also depends on what is the scale of your roughness with respect to diameter. So this basically means that whatever length scale, relevant length scale of the roughness of the tube is 0.004 times diameter. Okay. So that can of course cause a lot of friction losses. So based on that, but we will, for the most part, use this part where we'll say, okay, F is 0.079 to the Reynolds to the 1 over 4. Okay? So this is something that we will write down. So basically, going back to sketchbook. For 13. So basically, for laminar flow, we know Vz, okay? Vz is actually P0 minus PL R squared divided by 8 mu L. So when you plug that into the friction factor definition, I'm not going to go through it, but you will get that 16, it's 16 over Reynolds, where Reynolds number is d rho Vz divided by mu. So that relationship is obvious and it's sort of as expected. For turbulent flows, so basically this is for Reynolds number less than 2100, okay? This part. Okay? For turbulent flows, analytical analysis is much more involved. And we are not going to go into it, but it's for smooth tubes, we will use F is 0.0791 divided by Reynolds to 1 divided by 4. And this is for 2100 less than Reynolds less than 10 to the 5. Again, this is correlation extracted or fitted to from experimental data. So once we have this, again, once we have these correlations, we assume them as known. If I'm building a system that has piping with expected turbulent flow, I will assume the friction factor is a form of this. Maybe if I know that I have rough tubes, I'm going to change it up slightly. And once I know that, then I can predict what my pressure drop is going to be in that pipe. So basically that dictates how I'm going to build my system. Okay, so this is flow in tubes. Now we have flow around the sphere, and that's something that we actually slightly looked into already last time as a small exercise in class, but let's define it strictly. Or flow, basically more general flow around submerged objects. Sphere is representative of that. So in flow in tubes, it was customary to take the vetted perimeter. In submerged objects, you're not going to necessarily take the vetted perimeter, but you're going to take the projection of your object. And that's often for practical reasons, because as you're flowing towards an object, okay, because of the flow around the object, if that object is actually, for instance, something like ellipsoidal, okay, what's more important is basically this cross-section rather than the entire area of the object, because you have very different, like flow has stagnation points before and after the object often. Okay. So it's not the entire area of the object that is all that important in the flow. It's also much easier to measure practically this projection than it is to know the entire area of the object. So it's more often to correlate things using, because I will often, in practical, for instance in soil science, you will do sieve, and sieve size tells you diameter in some direction of that object. So that's your projected diameter of whatever object you're sieving, and the rest of the dimensions you kind of forget, right? So you might have had something oblong or so forth, you're still going to go with the diameter that you get from the sieve. So it's typical to actually do a projected area. So it's a customary to take this area, okay, is area obtained by projecting (3D) object onto a plane perpendicular to approach velocity. Okay. So for sphere, that's going to be r squared p, however it is that I'm approaching the sphere, whatever the direction might be. And by the same token, the energy density that I'm going to look into is 1/2 rho v infinity square, where v infinity is approach velocity before I actually hit the object, so away from the object. Or sphere in this case. Now, if I have I'm looking for that kinetic portion of the force, right? And if I have laminar flow around the sphere, I know Stokes' formula, and I know precisely then what the kinetic portion of the force is, right? But if I don't have laminar flow, then I'm going to again look into the macroscopic balance. And again, other than just looking at the approach velocity to the object, I'm going to assume that my object is slowly falling through the sphere, through the fluid, and object has achieved the terminal velocity. So at terminal velocity, I know that I have a force balance. Okay? So basically, what will actually go into the definition of Fk, okay, is gravitational force minus buoyant force, assuming the object is falling through fluid so I'm going to do this. Fluid and has achieved terminal velocity. So that is something I can measure. If I have laminar flow, I actually have analytic expression so I can compute. But if I don't have laminar flow, then I can measure this force simply from the force balance. So basically I'm going to have that this is 4/3 p r cubed. So my gravitational force is rho. I'm going to define it as rho s, rho sphere, rho solid, and g. So this is volume times density times g. So that's simply mass times gravity. And my buoyant force is the same, but just for the fluid. So that this is weight of the displaced fluid. So this This is solid, and this is fluid. So then my V infinity is taken as this terminal velocity. So when I plug into this information, I actually now plug into my definition for friction factor. Okay. Then my friction factor has to, by definition, be Fk divided by AK. So that is my 4,3 PR cube G, rho solid minus rho fluid, divided by area is R squared P, and then 1/2 rho VT squared. So that is 4 divided by 3G. We often again put diameter here. VT squared, rho solid minus rho fluid, divided by, wait a second, this is rho, I'm like, what is this? This is rho fluid. Okay. So this is a definition for friction factor around sphere okay. Again, it's computed from experimental measurements of terminal velocity for falling sphere. So I measure this, I know this, I know this, I know this. Okay? And just as we showed last time, if in fact my flow regime is laminar, then Fk is what? Stokes. So what is Stokes? Vt or V infinity? Right? So when I plug that in, I would get that F is 12 mu over R rho V infinity, which is 24 over Reynolds number for sphere. So that's laminar. Good. So again, this is basically how flow around the sphere looks like. Technically, laminar flow regime, strictly speaking, is for Reynolds number less than 0.1. Okay. And then at larger Reynolds numbers, we're going to have different flow properties. Have you, there's actually a book, it's called Visualization of Flows, Milton Van Dyke. I'll bring it with me next time. It has like a lot of images like this from literature. And basically when you correlate up until Reynolds number 1, you can use F is 24 over Reynolds. After that, we have a slightly different functional correlation. Again, it's a correlation, so all of these numbers, this is something that is fitted to experiments. So basically for large Reynolds number, we have this square root of 24 over Reynolds plus 0.54 and then square. So this is what we use for non-laminar regime. All right. We will go to friction factors for sphere packs on Wednesday.